Now we will discuss vector valued integration. So let V a non-linear space, we will discuss over R, and let us take phi from say 0, 1 to V, a given function. We will talk of continuous functions, but let us say. So we want to give a meaning to this expression 0 to 1 integral phi t dt. So what meaning to this? How do you define such an integral? Okay, so suppose you had just a real valued function. What would you do? You would take a partition of 0, 1. So P partition of 0, 1. So we have 0 equals x naught less than x1 less than xn equal to 1, and then you would assign SPF, which is a Riemann sum associated to this partition, which will be sigma I equals 1 to n f of ti delta xi, where delta xi is xi minus 1. And then using some suitable limit process, we would define the integral. So suppose we do the same thing. Now of course delta xi must be written in the front, because f of ti is a vector and delta xi is a scalar. So we will write here delta xi into f of ti, where ti belongs to the interval xi minus 1 xi. So this notation is a bit faulty, but it does not matter. It does not take into account which t's we are talking about, but we want. So if we take a limit and we are able to define the integral, then if f is any element of V star, then f of SPF will be sigma I equals 1 to n delta xi. So now we are sorry, we should have had phi here. Okay, so phi again. So this is f of phi ti, and then we pass on to the limit. So if we can go to the limit, f is continuous, so this will go to f of y. So y is the integral, so integral is a vector in V, and therefore this will go to f of y, and this will be equal to, but this is nothing but a continuous function. So if phi is continuous, so let us assume now phi is continuous. I think we will stop. Okay, we will now discuss vector valued integration. So let us take V to be a nonlinear space over R, and let phi, for instance, be a function from 0, 1 to V, let us say continuous. So we want to know, give a meaning for integral 0 to 1 phi t dt. Okay, so what do you do if V equals R, for instance? If V were R, you would have taken a partition P of the interval 0, 1. So this will be 0 equals x naught less than x1 etc. less than xn equal to 1. Corresponding to the partition, you would define the Riemann sum SP phi, which will be sigma delta xi times phi of ti, where ti belongs to the interval xi minus 1 xi, and you have delta xi is equal to xi minus 1, and then you would take a limit. If you did the same thing now, this will become this is a vector in V, and therefore when you take a limit in V, you will get a vector in V. Therefore, integral, if it exists, will be a vector in V. Okay, let us assume the integral exists. So let us call that integral as y, which belongs to V. Okay, so now let f be any continuous linear functional. Now when you pass to the limit here, if this converges to the integral, so this will converge to f of y. And so you now apply f on both sides. So if you will get f of phi of t of y, and this will now converge to f of y. On the other hand, this is nothing but the Riemann sum for the continuous real valued function f composed with phi, and therefore this should converge to integral 0 to 1 f of phi of t dt, and therefore these two should be equal. So we are going to make a definition. So V norm linear space and phi a mapping from 0 1 into V. So we assume that 0 1 is given the Lebesgue measure, so I am not specifying it here. Okay, the integral 0 to 1 phi of t dt, if it exists, of course this is not at all guaranteed, is a vector y in B such that for every f in B star, we have f of y equals integral 0 to 1 f of phi of t dt. So this is what we mean by the integral, and this is the meaning which we give. So it should be a vector such that for any f in V star, the integral, it should be equal to this real valued integral here. Okay, so now let us prove the following theorem or proposition. Proposition V real Banach space and phi from 0 1 to V continuous. Then integral phi of t dt 0 to 1 exists. So proof. Okay. So 0 1 is compact, phi is continuous, implies phi of 0 1 is compact. Continuous image of a compact set is compact. So this is compact in V. Okay. So now you take H to be the convex hull of phi of 0 1. So that means it's the smallest convex set which contains this image. And then since V is complete, H closure is compact. So this is a topological fact which I will not prove here, we will accept this. So if you have a complete normally a Banach space, so, and you have a convex and you have a compact set K, then the closure of the convex hull of K is also compact. So that is the so V Banach, K contained in V compact, then H equals convex hull of K, then H, so and this will imply that H closure is compact. So in fact, because of the completeness, it is enough to show that H closure is totally bounded, and that can be done. Okay, anyway, we will accept this result. So we will assume this theorem in topology, and we will just take it. Okay, so now let L be an arbitrary collection of continuous linear functionals, L finite. So it's an arbitrary finite collection of continuous linear functionals. So you define E of L equals set of all y in H bar such that f of y equals integral 0 to 1 f of phi of t dt. So this y satisfies the condition of being the integral of phi of t, but only for finite number of linear functions, not for everything. So our aim is to find a y which does it for every linear functional, but we want to so we will start with this EL. Okay, so then claim, so EL obviously closed. So if you take any yi, the right hand side is always the same, and therefore for a fixed linear functional. So if you have yi converging to y, f of yi is a constant sequence, so it will always converge. So it is obviously a closed set. So first step, EL is not empty. So we are going to show that this is never an empty set. So given any finite collection, you can always find a common vector such that equality holds. So let us take L equals F1 to Fk. Now I am going to define A from V to Rk, linear map, A of x equals F1x Fkx. So A is obviously continuous because each of these coordinates is continuous. So A continuous linear. So H closure is compact, we know. So this implies that A of H closure, let me call it K, is compact. So assume there is a vector T1 to Tk which is not in K. So I have a compact, and this is also because H closure is convex, A is linear, therefore this is also convex. So K is a compact convex set. T1 to Tk is a singleton, which is also a compact convex set if you like. So by Hahn-Banach, there exists a linear functional on Rk such that linear functional, let me call it capital F, because I don't want, okay, such that capital F of Z is less than capital F of Z1 Zk is strictly less than capital F of T1 Tk for every Z1 Zk in K. That is just the Hahn-Banach theorem. Okay. So, but what is a linear functional on Rk? Dual of Rk is itself, and a linear functional is just a linear combination of these things. That is, there exists C1 Ck reals such that sigma I equals 1 to k Ci Zi is strictly less than sigma I equals 1 to k Ci Ti. So, this is just the linear functional capital F. Okay. So, that is all the same. And in particular, if T belongs to 0, 1, you have sigma I equals 1 to k Ci F of phi I t is strictly less than sigma Ci Ti, because F of Fi of it, Fi of it, that is the phi is a single function Fi, because A is what, the mapping F1 F2 Fk, and its image is K. Okay, image under H bar is K. So, therefore, this is true. So, now let us integrate this. Therefore, sigma I equals 1 to k Ci Mi is strictly less than sigma I equals 1 to k Ci Ti, where Mi is nothing but the integral from 0 to 1 Fi phi of t dt. Okay, so what does this mean? So, in other words, if T1 Tk is not in K, then T1 Tk is not equal to M1 Mk. So, this implies that M1 Mk must belong to K. But what is K? K is nothing but the image under the A of H bar. So, therefore, that is, there exists a y in H bar such that Fi of y equals Mi, and that is equal to integral 0 to 1 Fi phi t dt. So, this is true for all 1 less than to I less than to k, and that is y belongs to EL. So, EL is non-empty. Okay. So, now next step, so let I be a finite indexing set. Okay. And then you take Li for I in I, finite collection of linear functionals in V star. Okay. Then you take L equals union I in I, Li. So L is also finite because each of these is finite and this is a finite union, and therefore L is also finite. Okay, and it is very easy to check that intersection I in I, E of Li is nothing but E of L. Okay, so this is obvious and therefore this is not empty by step 1. Therefore, we have shown that EL, this family L finite subset of V star, it has finite intersection property. What does it mean? But H bar is compact, implies intersection over all L finite subset of V star, EL is non-empty. So in particular, for every F in V star, you set L equals singleton F. Therefore, there exists a Y in intersection L finite subset of V star EL, that is, for every F in V star we have f of y equals integral 0 to 1 f of phi t dt, that is y equals the integral 0 to 1 of phi t dt. So this proves that for continuous functions you always have the integral. Okay, very good. So now one of the important properties of the integral in one dimensions, for instance, if you have phi from 0 1 to r and you take integral 0 to 1 phi of t dt and you take the modulus. When you want to estimate this integral, the first thing you would write is integral less than or equal to integral mod phi t dt. So we want to generalize this to vector value integration, because this is a very important estimate. So whenever we want to estimate the norm of an integral, this is the first step which we will do. So proposition V real norm linear space, phi from 0 1 to V continuous, then norm of integral 0 to 1 phi t dt, remember this is a vector in V and therefore I can talk of its norm, is less than or equal to integral 0 to 1 norm phi t dt. So just taking the modulus inside, you can take the norm inside, and this is a real valued integral, and therefore you don't have to worry about it. Okay, so proof. So again this is an application of the Hahn-Banach theorem. Okay, so there exists f in V star, norm f equal to 1, such that norm of integral 0 to 1 phi t dt is equal to f of integral 0 to 1, and therefore this is equal to integral 0 to 1, by definition of the integral, this is f of phi t dt, which of course is less than or equal to integral 0 to 1, we take the real, since the real valued integral now, f of phi t dt. But what is mod f of phi t? F is a continuous linear function, this is less than or equal to norm f into norm of phi t dt, and norm f is equal to 1, so that you do not have to worry, and then you have proved this result. Okay. So we have done integral 0 to 1, but you can do this in any interval. For instance, suppose I have, so remark, suppose phi is from AB to B continuous. How will I define the integral? In the same way, you can define it like this, or you can define phi, define psi from 0 1 to B, where psi of t equals phi of A plus t times B minus A. So psi of 0 will be phi of A, psi of 1 will be phi of B, and in between psi gets mapped. And we define integral A to B phi of t dt by change of variable. So this will be B minus A times integral 0 to 1 psi t dt. And you can check all the properties, both the properties, namely integral. So for every f in V star, you have f of integral A to B phi, this is equal to integral A to B f composed with phi, and also norm of integral A to B phi is less than or equal to integral A to B norm of phi. So both these you can check yourself. Okay. And then now assume phi is from 0 infinity to B continuous. Assume limit as lambda tends to infinity, integral 0 to lambda phi t dt exists. What does this mean? You take any sequence lambda n with lambda n tending to infinity, then limit n tending to infinity integral 0 to lambda n phi t dt exists, and limit is independent of the sequence chosen. So this is the meaning of the statement. Okay. So then we define, define integral 0 to infinity, the improper integral if you like, is equal to limit lambda tending to infinity integral 0 to infinity lambda phi t dt. Once again, for every f in V star, f of integral 0 to infinity phi t dt will be equal to integral 0 to infinity f of phi t dt, and norm of integral 0 to infinity phi t dt will be less than or equal to integral norm phi t dt 0 to infinity. You can automatically see that all these exist, and this will be the norm. You can define the integrals over other kinds of infinite intervals in a similar way. Okay. And the last thing which we want to do is, now let us, so another example if you like of existence of an integral. So the integral we will, so let us take x s mu to be a measure space. So that means x is a set, S is a sigma algebra on X and mu is a measure. Okay, and then we have the Lebesgue measure of a function. Okay, so now you look at phi from V to from X to V. We say phi is weakly measurable if the map X in capital X going to f of phi of X in R is measurable. It's a real valued function, is measurable for every f in V star. Okay. So now let us assume two things. One is we assume that phi is weakly measurable to integral over X norm phi of X d mu of X is finite. So the mapping X going to norm phi of X is a real valued function, is integrable. And then 3, V is reflexive. So then integral over X of phi d mu, or if you like integral over X phi of X d mu of X, depend, you do not have to, since there is no confusion, you do not have to write, exists. Okay, so why? So let us take any capital F in V double star. Sorry, no, let's not take that. So let us define for F in V star lambda of F equals integral over X f of phi of X d mu X. You compose it with phi, you get a real valued, it is a measurable function, so I can define this. So what about mod lambda F? This is less or equal to integral over X mod f of phi of X d mu of X, that is less than or equal to integral over X norm F norm phi of X d mu of X, and therefore that is less than or equal to integral over X norm phi of X d mu of X times norm F. And so this we have assumed is a finite quantity, and therefore lambda belongs to V double star. It is a continuous linear function. V is reflexive, that means lambda is to be the evaluation function. So V reflexive implies there exists a y in V such that lambda of F equals f of y for every f in V star. That is f of y equals integral over X f of phi of X d mu of X for every f in V star, and that is exactly saying that y is the integral of phi. Okay, so that is by definition y will be the integral phi of x d mu x over x. Okay, so we will stop with that. Thank you.